Dear students, we are solving a problem in the last class, that is g of s h of s equal to 100 divided by s power 5. Whenever we are having poles at origin, or if we are having a pole at origin, the Bode plot will be having the slope minus 20 dB per decade. Whenever we are having the zeros in the transfer function, the Bode plot slope will be increased by plus 20 dB per decade. Keep in mind that here in this problem we are having 5 poles at origin, that is s power 5. So if you are having s power 5, for each pole the Bode plot slope will be having minus 20 dB per decade for each pole, and for each zero will be having Bode plot will be having plus 20 dB per decade. So here 5 poles are there at the origin. So the Bode plot slope should be minus 20 dB plus minus 20 dB minus 20 dB minus 20 dB minus 20 dB, that is 5 times of minus 20 dB is nothing but minus 100 dB per decade. The magnitude in dB is minus 100 dB per decade. Pi equal to angle equal to, for each pole the Bode plot will be having, the angle will be having minus 90 degrees. Since 5 poles are there, so minus 450 degrees. Shift in the plot is 20 log 100. 20 log 100, that is 20 log k, that is 40 dB. If you plot this is the magnitude plot for this problem. Plus 100, here 1 is there, if k equal to 1, we need to shift it by plus 40 dB. Since we are having here 100, 20 log, what is the magnitude formula? Magnitude in dB formula is 20 log of g of s h of s, that is 100, that is this 100 can be 10 square, this 10 square, 20 log of 10 square, 20 log of 10 square is nothing but 40, 20 log of 10, 100 is nothing but 40 dB. So plus 40 dB will be shifted upward, since this 100 is we are having in the numerator. The next problem, g of s h of s equal to s power n. Whenever poles are present, whenever zeros are present, then the magnitude in dB is plus 20 n dB per decade. The angle is plus 90 n degrees. See, the magnitude plot is, can observe here, the magnitude plot is this, minus 20 n, here 1, plus 20 n dB per decade. Here the magnitude is minus 20 n. At 1 it is 0. About the slope of this line, plus 20 n dB per decade. The angle is plus 90 degrees. Whenever poles are present, that is in the denominator, if s power term is there, then the magnitude in dB is minus 20 dB per decade. If one pole is present in the denominator, that is minus 20 dB per decade. If n poles are present in the denominator, then minus 20 n dB per decade. The slope magnitude will be minus 20 n dB per decade. Yeah, the next problem. If g of s h of s equal to 1 divided by s tau plus 1, then the first step what we need to do, we need to replace wherever s is there j omega, find out the magnitude and find out the magnitude in dB. To find the magnitude in dB here, minus 20 log of under root of 1 plus omega tau whole square. The actual angle is, how can we find the actual angle? Here for this also tan inverse angle of 1 divided by angle of under root of this. So for this tan inverse of omega tau. Now for this, in this case, asymptotic or approximated analysis. We are going to consider two cases in this case. The first case one is omega tau. Omega tau is less than 1. If omega tau is less than 1, neglect omega tau. If you neglect omega tau, then omega can be written as omega is less than 1 by tau. So asymptotic magnitude is 0 dB per decade and asymptotic angle is 0 degrees. Case 2. When omega tau is greater than 1, if this is greater than 1, we will be neglecting 1. So omega can be written as greater than 1 by tau. Asymptotic magnitude is minus 20 log of omega tau. This can be written as minus 20 log omega minus 20 log tau. That is log AB can be written as log A plus log B. Slope, the slope is dm by d log omega, that is minus 20 dB per decade. Hence the phase angle, asymptotic phase angle is angle 1 divided by angle j omega tau, that is minus 90 degrees. Now here the main important to plot Bode plot. For plotting the Bode plot, the main important term is corner frequency. The frequency at which slope changes from one level to another level. Corner frequency is the frequency at which the slope changes from one level to another level. Corner frequency is nothing but finite poles, finite zeros located in the form of magnitude. You can observe here, for n finite poles at s equal to minus 1 by tau, below corner frequency the magnitude is 0 dB per decade. Please keep in mind that. For n finite poles at s equal to minus 1 by tau, below corner frequency the magnitude is 0 dB per decade. For n finite poles at s equal to minus 1 by tau, less than corner frequency is the slope is 0 dB per decade, the phase is 0 degrees. Greater than corner frequency is minus 20 n dB per decade and the phase is minus 90 degrees n. This is very important for corner frequency, where in the Bode plot where the slope has to change at the corner frequencies. Errors in the plot. Actually the error is nothing but asymptotic minus actual value. Error at omega equal to 1 by tau. Actual magnitude is minus 20 under root of 1 plus 1, that is minus 3 dB. If you are going to substitute omega equal to 1 by tau, 1 plus omega tau, if you replace omega equal to 1 by tau, tau will get cancelled and we left over with under root of 1 plus 1. That this can be simplified as minus 3 dB. Asymptotic magnitude equal to 0 and error equal to 0 minus of minus 3 dB, that is 3 dB. For nth order transfer function, the error is 3n dB. Substitute here different values of tau. You will be getting it as corresponding errors. The error is maximum at corner frequency. The error is decreased symmetrically with respect to corner frequency, either above or below corner frequency. See here, at 0.5 by tau, the error is minus 0.96 dB. At 1.5, the error is 3 dB. At 10 by tau, the error is 0.4 dB. At 0.1 tau is 0.04 dB. This is the magnitude plot and this is the angle plot. Even for the angle plot also we will be having some errors. Yeah. If the problem is in this type, g of s h of s equal to 1 plus s tau whole power n. I told you that if poles are present, then the magnitude, the Bode plot slope will be minus 20 dB per decade. If zeros are present, plus 20 dB per decade. So here a 0 is present, n zeros are present. So we will be getting the slope of Bode plot will be plus 20 dB per decade magnitude. That is what is the corner frequency. To find out the corner frequency, write down this in the form of s plus something, whatever you get it as. What irrespective of in the problem, whatever they will be given. In this case they had given 1 plus s tau. Write down this s plus 1 by tau. So the corner frequency is 1 by tau. So the slope of Bode magnitude plot is plus 20 dB, plus 20 n dB per decade. If the slope is less than corner frequency 1 by tau, less than corner frequency, the slope is 0 dB per decade. The angle is 0 degrees. If it is greater than corner frequency, plus 20 n dB per decade, plus 20 n dB per decade, the angle is plus 90 degrees, plus 90 degrees. Now let me see some example for this type of problem. G of s h of s equal to 10 into s plus 2 into s plus 10 divided by s square into s plus 5 into s plus 10 s plus 50. For this, represent in the form of corner frequencies. If you represent this in the form of corner frequencies, we can write it as 10 I have written here, 2 had made a common 2, and here also 10 is there, I had made a common, so we can write as 1 plus s by tau into 1 plus s by 10. In the denominator also, yes, 50 is there, I had made a common 50, and here 5 is there, we had made a common 5. Here s square, 1 plus s by 5 into 1 plus s by 50. Now if you simplify this, the magnitude will be getting 0.8 like this. The initial slope of the plot is given by poles and zeros which are located at origin. What should be the initial slope? Here how many poles are there? 2 poles are there at origin. How many zeros are there at origin? There are no zeros at origin. So if 2 poles are present at origin, then the initial slope should be, if pole is present, then 1 pole is present at origin, then minus 20 dB per decade. If 2 poles are present at origin, then minus 40 dB per decade. You can observe here minus 40 dB per decade is there. Minus 40 dB per decade. So